The derivative of a vector function, r of t, is defined as the limit of delta r over delta t as delta t goes to 0, which you could see written out over here. Okay? We don't really use the definition much. We'll eventually just start using rules, which you could see over here, so that if you want to take the derivative of r of t, well, in a sense, the derivative and the components commute in that the derivative of the vector valued function is the derivative of each of the components. Okay? But this definition, the ratio there, is still important in understanding what's going on when we take the derivative. If we have the vector function giving us this vector in green at time t equals t, then at a later time delta t, at some later time delta t, so that we're at t plus delta t, then we're going to have this purple vector there. Okay? So the difference between these two, r of t delta t, t plus delta t minus r of t, is going to be this red vector. Now, what are we doing when we're taking the derivative? We're taking the limit as delta t goes to 0. So as this purple point gets closer and closer to t on the t-axis, so we're taking this vector here and dividing it by delta t. What we should get at the end, as we move closer, is a vector that is tangent to the curve and has the magnitude given by this ratio, or rather the magnitude of the ratio. This translates, though, once we are comfortable with this definition, we can show that all we really have to do to get the derivative of a vector valued function is just take the derivative of the components. So let's take a closer look at how this derivative works. Here we have the vector there. This is the vector r, okay? The value of the vector function at different t. So suppose we're comfortable at this one t that we chose over there. Then for delta t, we have at a later time the vector oq, okay? That's the second vector that you see there. And we can make this get closer by making delta t smaller, as you see there. And the difference between these two is this vector pq, okay? That's the delta r. Now, what's going to happen when we divide that by delta t, take delta t and divide it by delta r, we get that red vector, okay? That red vector now is the vector delta r over delta t. And as we make delta t smaller and smaller, we see that delta r, the green one, just goes to 0 as it should. But in red, the ratio still is finite. It doesn't go to 0, so let's just get rid of the delta r. And now you could see delta r over delta t. And we take that limit as delta t goes to 0. And we get the red vector. Something extremely important to pay attention to is that r prime is tangential to the curve. Okay? It touches this curve at this point and is tangent to it. That is something to pay attention to, since whenever we need a vector that is tangent to a curve, we will use the derivative. So let's go ahead and actually compute a derivative of a vector function. Here we have the vector function with x component e to the minus t, y component 10 square root 2, and z component 2 cosine 3t. And we're just going to take the derivative. You're going to take the derivative of each component. Simple as that. So the derivative of the first component, e to the minus t, is just going to be negative e to the minus t. And what's the derivative of the 10 square root of 2? We'll do that up here. Why not? So the derivative of 10 times t to the 1/2, which is the same as square root of 2, you just use the power rule and bring down the 1/2, and you're left with t to the minus 1/2. And so you could write that as 5 over root 2, because t raised to the power of minus 1/2. And you could take the derivative also of this, and we end up with a vector. Don't forget that just because we were writing this as a sum, ultimately it's a vector. We could have left the answer the same way that it is down there, but we could have also written it this way. You should be getting comfortable by now using both notations for a vector. So this is the same as that. And just something to note that r of t is defined for t greater than or equal to 0. Okay, so this square root of 2 doesn't let us put a negative t in there. We're dealing with real functions. On the other hand, when we take the derivative, we see we get into a problem when t equals 0. So although this function is defined and continuous, in fact, for t greater than or equal to 0, it must exclude 0 once, for it to be differentiable. So it's differentiable only for t strictly greater than 0.